Welcome back, dear all participants. Hope you have learned many things from the first two technical sessions. In this third session, we have with us Dr. Devegowda Kalita, Assistant Professor, Department of Mathematical Sciences, Tezpur Central University, Assam. Welcome, sir. On behalf of all participants, I thank you for accepting our invitation to speak at this international webinar. So, sir, before going to you, I request Ms. Shilpa Madam, Department of Computer Science, to introduce you to our participants.
Thank you, Vijay sir. I hope I'm audible and visible to everyone. Good afternoon to all and welcome back to this afternoon technical session. So please confirm, am I audible, right?
Yeah, you are audible.
Yes, okay. Yes, you are audible. Yeah.
So good afternoon to one and all and welcome back to this session. It's my privilege and honor to introduce the resource person, Dr. Devegowda Kalita. Dr. Devegowda Kalita completed his MSc in Mathematics from Guwahati University, Assam. He obtained his PhD from IIT Guwahati for the research on spectra of weighted directed graphs under the supervision of Professor Sukata Pati. Dr. Devegowda is currently working as Assistant Professor in the Department of Mathematical Sciences, Tezpur University, a central university situated in Assam. His research interests lie in algebraic graph theory. Dr. Devegowda is currently supervising 3 students towards their doctoral degrees and 1 student has been awarded PhD. Dr. Devegowda so far has published 17 research articles in journals indexed by SEIE, with several of them being the pure mathematical journals, such as Linear Algebra and its Application, Linear and Multilinear Algebra. With over 150 Google Scholars citations, Dr. Devegowda serves as the referee of several SEIE journals like Electronic Journal Electronic Journals of Combinatorics, Linear Algebra and its Applications, Linear and Multilinear Algebra, Applicable Analysis and Discrete Mathematics, Electronic Journal of Linear Algebra and Special Matrices. To his credit, Dr. Devegowda successfully completed a major research project under matrices funded by the Department of Science and Technology, SERB, the Government of India. Apart from an active researcher, Dr. Devegowda loves teaching graph theory, topology, discrete mathematics, and analysis. So it's a great privilege and honor to our institute that Dr. Devegowda Kalita accepted our invitation, and today he'll be talking on algebraic connectivity and Fiedler vectors of graphs. On behalf of the organizing committee and all the participants, I heartily welcome for this technical session, and I heartily thank you for accepting our invitation. So now I request you to take over the session, sir. Thank you very much.
Thanks, Shilpa, for your introduction. And also I thank HT Devegowda College for inviting me to give a talk in this webinar. So my title will be algebraic connectivity and Fiedler vector of graphs. So before we discuss about algebraic connectivity and then Fiedler vector, we need to have some definitions, and so there are several matrices associated with a graph that all of us know that. And one such very popular matrix is known as the adjacency matrix of a graph. What is the adjacency matrix of a graph? The adjacency matrix of a graph, if G is a graph on n vertices, is nothing but an n by n matrix. N by n matrix whose ith entry is defined like this. Aij will be 1 if I and j are adjacent. Adjacent means the vertices I and Z, between them, there is an edge. Otherwise, if there is no edge between I and Z, otherwise Aij is 0. That is the simple definition of adjacency matrix of a graph. Here is an example. We take this graph G, and this is the adjacency matrix. Here we can see the diagonal entries are all 0. This is as per the definition, and we are talking about simple graph only. Our discussion will be based on simple graph where we don't have loops and all other things. And one can see that this 1, 2, the 1, 2, and 3 is 1 because there is an edge. And similarly, 2, 1, and 3 also is 1. Okay. Since these are undirected graphs, so this matrix is symmetric because we have simply A12 is same as A21. And one can see that there is no edge between 2 and 4. So the 2, 4, and 3 is 0 here, this matrix. One can easily see the rest of the entries of the matrix from the graph itself. Then the next important matrix, important means it is very popular matrix known as the Laplacian matrix of a graph. The Laplacian matrix of a graph is simply defined to be the matrix dg minus ag. So from ag we define the Laplacian matrix. What is dg? dg is simply the diagonal matrix where the ith diagonal entry will be the degree of the vertex I in the graph. So dg is a diagonal matrix. Lg is simply dg minus ag. Here is an example. We take this graph G. This is dg. Degree of 1 is 2, degree of 2 is 3, degree of 3 is 2, and so on. So this is my dg, the diagonal matrix where on the diagonals I have degrees. And Lg is simply this. So one can see the Az, and then I just obtain Lg to be dg minus, which can be seen as this matrix. Now this matrix, the first property that this matrix have is this matrix is singular. And that can easily be seen. One can see that the number of ones in a row I of the adjacency matrix is equal to the degree of the vertex Pi. Okay, if my vertices are say P1, P2, Pn, then degree of Pi is simply the number of ones in row I. And therefore, the sum of the entries in row I of the Laplacian matrix is 0 for any I. Because in the Laplacian matrix, non-zero entries are minus ones only. Okay, just these ones becomes minus 1 in Lg. And on the diagonal, we have the degrees. So that's why the sum of the entries in row I of the Laplacian matrix is 0. So that's why 1, this notation 1, this is a vector where all the entries are 1. So because the sum of the entries of Lg are 0, this 1 is an eigenvector of the matrix L corresponding to the eigenvalue 0. And that says that this Lg is singular. In fact, from here only we can say, because the sum of the entries in the row I Lg is 0, so I can say the rows are linearly dependent. It's singular. So the factor of all ones is an eigenvector corresponding to G. That is crucial in our talk. So 0 is an eigenvalue and Lg is singular. Now, what is a cofactor? And this this is a very crucial property of the Laplacian matrix. What it says, all the cofactors of LG are equal. Now, what is a cofactor? Let me define. So by this notation, we mean the n-1 by n-1 submatrix of L obtained by deleting ith row and z column. Okay, the cofactors of L are simply this quantity, -1 to the power I plus z, and determinant of this type of submatrices. These are the cofactors. So for any ij, these numbers are all equal. That is what this Laplacian matrix. So let me give you a rough idea how it follows. So we all know that adjoint of a matrix is like this. Adjoint of L is the n by n matrix with ij entry, these cofactors. So the adjoint of L entries are just the cofactors. Right? Now we also know that L times adjoint of L is simply determinant of L times I, but determinant of L is 0. So L times adjoint of L is 0. Therefore, LA is equal to 0 for every column A of adjoint of L. Because adjoint of L is a matrix. L times this matrix is 0. So L times every column of this matrix, L times every column of this is 0. Okay. So now the rank of a matrix, we all know that is equal to the size of a largest square submatrix having non-zero determinant. That we all know. Okay. Now since determinant of L is 0, we see that rank of L is less than n. And observe that the entries of adjoint of L are nothing but the determinants of all possible n-1 by n-1 submatrices of L. Right. So this follows that rank of L is less than or equal to n-2 if and only if adjoint of L is 0. Right. So on the other hand, if rank of L is n-1, then the dimension of the null space is this much. That is, LA is 0 if and only if A is a multiple of the factor of all ones. That is, entries of A are all the same. And that is the case for every column of adjoint of L. Right? So, adjoint of L will be a matrix like this. All the entries here are same. But at the same time, we also know that L is symmetric. So, adjoint of L is also symmetric. And therefore, A1 will be A2. Right? Then we can say that A1, A2, all these ANs are equal. Right? That means adjoint of L, entries of the adjoint of L are the same. Hence, the cofactors of L are all equal. This is how the proof goes. Now, this is the very crucial theorem, matrix tree theorem. Now, what it says, see, we have already seen that the cofactors of L are all equal. But equal to what? Which number? That is very crucial and very interesting. That equal number is simply the number of spanning trees of the graph. How the properties of matrix is connected to the structure of the graph. This theorem was proved by Kirchhoff. Very long way. Okay. Now, what is a spanning tree? Spanning tree is a spanning subgraph which is tree. We all know that. Okay. And we will give a proof of that theorem. But before that, we need some more terminology. Now, what is an oriented graph? Say it is a directed graph D. We all know that consists of a finite non-empty set P of objects they are called vertices, and together with a set E of ordered pairs of distinct vertices. Okay. Here we have ordered pairs. So elements of E are called directed edges. That means if E, now ordered pairs means U, V, VU, they are different things. Now if E equals to U, V is a directed edge, then U is usually known as tail and the vertex P is usually known as head of the edge. Okay. Now suppose that G is a graph. It is not a directed graph. G is any graph. Okay, non-directed graph. Now what we do, we assign a direction to every edge of Z. And the resulting graph is a directed graph. And this directed graph, say D, is known as orientation of Z. Okay. This is an example. Here in the previous picture, we have seen that this graph, I just assign a direction to the edges, and whatever I get, this is a directed graph, and this is nothing but the oriented graph of the previous graph that I have shown to you. This is head. This vertex 2 is head of E, and vertex 3 is the tail of E. You can see from the definition. Okay. Now, what is a vertex edge incidence matrix? Okay. Now, suppose D is an oriented graph, okay, with the vertex set say V1, V2, Vn, and the edge set say E1, E2, Em. Then the vertex edge incidence matrix Q, the entries Qi, J, is actually an n by m matrix, and the entries are obtained like this. There I have done a mistake. There is a typo. Typo is like this. Here it should have been somewhere here. It should have been 0. Here Qij is 1 if Ei is the head of Ej. Uij is -1 if Ei is the tail of Ej, and otherwise it is 0. Means if I is not an n, Vi is not an n vertex of the edge Ej. Okay, there is type. Corrected is okay. So this is an example. This is the oriented graph, and here are the rows are indexed by the vertices, columns are indexed by the edges. And one can see that this is the vertex edge Laplacian matrix. This is Q. Theorem this says that rank of Q is n-1 for connected graphs of order. That is another nice property followed by this matrix Q. Rank of Q is n-1. Now suppose X is in the left null space of Q. So that means X is like this. Then one can easily see that Xi minus Xj equal to 0 because X transpose Q is 0. Then Xi minus Xj is 0 whenever I is adjacent to J. And therefore, Xu equal to Xv whenever there is an UV path. Okay, if U and V are two vertices and there is a UV path, since I get Xi equal to Xj whenever I and J are adjacent, so I can go like this Xu to the U2 V, say U, U1, U2, U3 up to say UKP. Then I will get Xu equal to Xu1 equal to Xu2 and so on. So that way I can find that Xu equal to X. Now since G is connected, we see that X1 equal to X2 equal to Xn. Because between any two vertices I can have a path. So if G is connected, so I can get every entry of X are equal. So the left null space of Q is at the most one-dimensional because they may be 0 also. If they are non-zero, then it is one-dimensional. Otherwise, it is two-dimensional. And therefore, rank of Q is at least n-1. And we observe that the column sums of Q are all 0. So therefore, rows of Q are linearly dependent, and that's why rank of Q is less than or equal to n-1. We know. So therefore, rank of Q is n-1. Now Q is another nice property. The matrix Q is totally unimodular. Now what is an unimodular matrix? A matrix is said to be unimodular if the determinant of any of its submatrix is either 0 or plus minus 1. Okay. So we can prove this statement using the method of induction, and we will try to prove it for any k. So k by k submatrix have determinant 0 or plus minus 1. Now for k equal to 1, the statement is clearly hold because the entries of Q are all 0 or plus minus 1. Therefore, for k equal to 1, the statement holds. Now assume that the statement holds for k minus 1. Now let B be a square submatrix of order k. Then each column, now if each column of B has a 1 and minus 1, then determinant of B is 0, because in that case, this column sum is 0, and that's why these rows are dependent. That's the determinant of B is 0. Okay. Now, if B has a 0 column, then also determinant of B is 0. So in these two cases, we have determinant of B 0. Now suppose that B has a column with only one non-zero entry, and that non-zero entry must be either 1 or minus. Okay, and you expand the determinant along that column. What do we get? And using the induction hypothesis, we can see that determinant of B is 0 or plus minus 1, because we have assumed that the statement holds for k minus 1. That means all k minus 1 by k minus 1 submatrix of Q has determinant 0 or plus minus 1. So in using induction, we can see that this Q is totally unimodular. And this is the most crucial property. L is Q transpose. The Laplacian matrix has a connection with this Q. Now, while defining Q, one can see that this Q is dependent on the this Q is defined on a oriented graph or directed graph. Now, Laplacian matrix is defined on a non-directed graph, right? So, suppose Z is a non-directed graph, and you assign any direction to any edge, whatever way you want, and you take the Q, the vertex edge incidence matrix, you will always find that L equal to Q transpose. That means this is independent of the orientation of the edges of the graph. Okay, so we will see how it is. See, observe that the IZ entry of Q transpose is simply this, from k equal to 1 to m Qik, Qjk. And for I equal to j, we have this. This is nothing but for k equal to 1 to m Qik whole square. Okay. And now note that this Qik is plus minus 1 if Pi is incident with Ek and 0 otherwise. Right? Therefore, Qik square is 1 whenever Pi is incident with Ek. That means this is equal to the sum of the degrees of the vertex I. And that is what the diagonal entries of this L. Okay. And now for I not equal to j, Qik times Qjk is not equal to 0 if and only if Qik is non-zero, Qjk is non-zero. That is trivial. And note that this Qik is non-zero and Qjk is non-zero if and only if Ek is an edge joining Pi and Pj. That is either Ek is this or this. That is Qik, Qjk is simply minus 1. And that is what we obtain. That means the IZ entry of Q transpose is simply degree of Pi if I equal to j. Otherwise, it is minus 1 if Pi is adjacent to Vj, and otherwise 0. That is what the Laplacian matrix. So finally, we obtain that L is Q transpose, and this will help us to see many other interesting properties of L. And in fact, now we are in a position to give a proof out, not proof, an outline of the proof of this matrix 3 theorem. Observe that we have just now proved L is Q transpose. Now, since all the cofactors are equal, so it is enough to find this This quantity, what does this mean? Okay. Matrix tree theorem says that all the cofactors are equal, not matrix, the cofactors gives you the number of spanning trees. And we have already proved that these cofactors are equal. So it is enough to obtain this determinant. This means from L, we just delete the vertex, delete the nth row and nth column from L. We try to try. Now using Cauchy-Binet theorem we have used here, we can see that this determinant is nothing but sum of the determinants of all n minus 1 by n minus 1 square submatrices of Q. And also note that these determinants of n minus 1 square submatrices are 0, 1 or minus 1. And it is non-zero if and only if n minus 1 columns of Q corresponding to the spanning trees of graph. The n minus 1 by n minus 1 square submatrix of Q is non-zero if and only if the n minus 1 columns of Q corresponds to a spanning tree, edges of a spanning tree of the. So that says that proof. Now, this is the most crucial property. The Laplacian matrix is positive semi-definite. How can we see? See, X transpose Lx is simply X transpose Q, Q transpose X, which is S. That's why this is for any X. So, this Laplacian matrix is positive semi-definite. That's why its eigenvalues are all non-negative. And of course, since this is a symmetric matrix, so its eigenvalues are real. So we can arrange the eigenvalues in this way. Lambda 1 is smaller to the largest. Lambda 1, lambda 2, and so on. And we know that 0 is an eigenvalue. So the smallest eigenvalue is 0. Now what about lambda 2? Can lambda 2 be also 0? The second smallest. And it can be when lambda 2 is 0 if and only if the graph is disconnected. Then only it can happen. Otherwise it cannot happen. That means if G is connected, then lambda 2 is always 0. And we can see this. Suppose that G is disconnected and say these are the components of G. And you observe that this LG is a matrix like this, block diagonal matrix. And one can easily see that this, now see this LG1, this can be treated as the Laplacian matrix of the component G1 itself, like that. So the factor of all ones is an eigenvalue of this corresponding to the eigenvalue 0. So you can say that 1, then these 0 components, this can be treated as an, not treated, it is actually an eigenvector of LG corresponding to 0. Similarly, x2 like this, x3 like this, xk like this, and all these are linearly independent eigenvectors of LG corresponding to the 0. So that means the multiplicity of 0 as an eigenvalue is k. That means if Z has k components, then the multiplicity of 0 as an eigenvalue is k. So if G is disconnected, that k is greater than or equal to 2. So I have lambda 2 is 0. Fine. Now conversely, we assume that lambda 2 is 0. Now observe that this M we can write like this. Ni minus M, I write this matrix, n minus 1 I minus L. And we can clearly see that this is a non-negative matrix because degree of a vertex here in the graph can be at the most n minus 1. That's why this is always a non-negative matrix. And from the Perron-Frobenius theorem, we can conclude that the algebraic multiplicity of the largest eigenvalue of an irreducible non-negative matrix is 1. Here is a typo. Irreducible non-negative matrix is always 1. That means the largest eigenvalue is simple of a non-negative irreducible matrix. And also note that the eigenvalues of M are simply n minus 1 minus lambda I. That can clearly be seen. And since lambda1 equals to lambda2 equals to 0, we see that the largest eigenvalue m is not simple. Because I have lambda1 is also 0, lambda2 is also 0. The largest eigenvalue of this matrix is not simple. That means the matrix M is not irreducible. Because if it is irreducible by Perron-Frobenius theorem, this largest eigenvalue should have been simple. So, since it is not irreducible, so I get a permutation matrix P like this. But then this matrix M is symmetric, so I can have B equal to 0. B equal to 0. That means PM P transpose is a matrix like this. But then it is a block diagonal matrix with at least 2 blocks. That means this LZ should have at least 2 components in the block diagonal, in at least 2 blocks, diagonal blocks. That means Z has to be a disconnected graph. That is the proof. So now what is an algebraic connectivity? Now from this theorem, we have seen that the second smallest eigenvalue is positive if and only if the graph is connected. So this second smallest eigenvalue actually gives you a measure of how the graph is, how much connected it is. So it gives something like that. So it has a connection with the connectedness. So that's why the name suggested, in fact, point as algebraic connectivity for the second smallest eigenvalue of the Laplacian matrix, and this was coined first by this Fiedler, M. Fiedler, Miroslav Fiedler. He has given this name, and he have seen this. He have actually proved this. He has proved. So the second smallest eigenvalue is positive if and only if Z is connected. So that says that this eigenvalue is related with the connectedness of the graph. It gives you some measure of connectedness. And an eigenvector corresponding to this algebraic connectivity is popularly known as Fiedler vector of Z. So we have now the definition of algebraic connectivity and the Fiedler vector. Okay. Now we will have some examples. Say for a complete graph, what is the algebraic connectivity? Let's see. We can see that this Laplacian matrix of the complete graph is simply Ni minus J, where J is the n by n matrix with all entries equal to 1. And we know that this 0 and n are the eigenvalues of J, where 0 has multiplicity n minus 1 and n has multiplicity 1. Okay, so the eigenvalues of this Laplacian of Kn are simply 0, n, and n. That means the algebraic connectivity of the complete graph is n. And one can see that this x1 is 1 minus 1 0 0, x2 is 0 1 minus 1, and so on 0 0 0 1 minus 1. These are the linearly independent eigenvectors of J corresponding to the eigenvalue 0. That is not difficult. You can easily see. That means these are the Fiedler vectors of Kn. So x1, x2, xn minus 1 are Fiedler vectors of Kn. Now, this Courant's theorem gives us this much information about this, which will be helpful for us. We know that this Laplacian is Q transpose. Now, suppose that X is a column vector like this, then we can see that Q transpose X at an edge E is simply Xi minus Xj whenever E is an edge between I and J. And therefore, X transpose Lx, which is this quantity, is simply sum of Xi minus Xj whole square whenever I and J are edges. So this sum runs over the edges of the graph. This X transpose Lx is equal to this for any vector X. And Courant's theorem tells us that this lambda 2, the second smallest eigenvalue, is simply minimum of X transpose Lx. And this minimum is taken overall X such that X transpose X equal to 1. That means X is normalized. And X transpose 1 is 0. Transpose 1 is 0. This is by Courant's theorem. And we will use this. Now, this theorem tells that the algebraic connectivity of two graphs, union of two graphs, is like this. Greater than or equal to this, where G and H are S disjoint graphs on the same vertex. And we know that this Laplacian of Z union H is simply this. You can easily see that. Therefore, the algebraic connectivity of G and G union H is simply minimum of this plus. And also we know that this quantity plus this is less greater than or equal to minimum of this plus minimum of this, but minimum of this is nothing but H plus H. And therefore, minimum of this, when minimum is taken over all X like this, I am having greater than or equal to H plus H, but this is equal to the algebraic connectivity of Z union H. Now, few consequences. Now, if H is a subgraph of Z, then I would always have AH less than or equal to AZ. The algebraic connectivity of a subgraph is always less than or equal to the algebraic connectivity of the graph G. Okay? H is a subgraph. How can we say this? See, suppose H is a subgraph of Z. Then what I do, see this, that what I will take, I will simply consider those edges of Z which are not in H as one graph, say H1. Then H1 union H gives us the graph Z, and we apply this previous theorem. This theorem. The algebraic connectivity of H1 union H, which is actually algebraic connectivity of Z, is greater than or equal to algebraic connectivity of H1 plus algebraic connectivity of H, which is obviously greater than or equal to algebraic connectivity of H. So that can easily be seen. Now, suppose that Z is a graph of order n, then Z is a subgraph of the complete graph Kn. That can easily be seen. Z is any graph, then Z is a subgraph of Kn. At the most, Z can be Kn, right? But we know that algebraic connectivity of Kn is n. Therefore, algebraic connectivity of Z is less than or equal to n, or any n. If Z is a graph of order n, then algebraic connectivity is always less than or equal to. Now, then we can ask the question, if G is not a complete graph, then can we have the algebraic connectivity to be also equal to n? The answer is no. This observation says that if H is a graph which is not a complete graph, and of course H is a graph of order n, then algebraic connectivity is always less than or equal to n minus 2. How can we see this? Now, suppose Z is the graph obtained from Kn by removing the edge 1 and 2, removing the edge between 1 and 2, right? So clearly, since H is not equal to Kn, we see that H is a subgraph of Z. At the most, H can be equal to Z. Okay? Therefore, AH is less than or equal to AZ. And if also you observe that this Laplacian of Kn is simply LZ plus that this matrix. And we know that this x1 equal to 1 minus 1, this is an eigenvector of Kn corresponding for the algebraic connectivity n that we know already seen. Therefore, LKnx equal to this plus, and this times x is twice x. So LZx equal to n minus 2x. That means n minus 2 is an eigenvalue of the graph G. Right? Since n minus 2 is an eigenvalue of Z, and the smallest eigenvalue of Z is 0, so the second smallest eigenvalue has to be less than or equal to n minus 2. That means algebraic connectivity of Z is less than or equal to n minus 2. So algebraic connectivity of H is less than or equal to n minus 2. That can easily be seen. Now, what is the algebraic connectivity of the complement of a graph? Okay. This algebraic connectivity of the complement of a graph is simply n minus the largest eigenvalue of the Laplacian. Why? Because we can see that LZ plus LZ complement is simply Ni minus J, where J is the matrix of all ones. Now let X be an eigenvector of LZ corresponding to an eigenvalue lambda not equal to 0. Then X transpose 1 is 0. That's what we all know. So now LGX equal to LG bar X is NX plus 0, which implies that lambda X plus LG bar X equal to NX, and that's why N minus lambda is an eigenvalue of LG bar, whose eigenvector is X. And therefore, AG bar is simply N minus rho G, where rho G is the largest eigenvalue. That can easily be seen. Now, let's come back to the algebraic connectivity of a tree, because trees are very interesting graphs that many people study, and there are a lot of applications. The algebraic connectivity of a tree is always less than or equal to 1 for any tree. It is always less than or equal to 1. And the equality holds if T is the star. This is due to Fiedler and Merrick's. Okay. And the algebraic connectivity of, among all trees, the algebraic connectivity of Pn is the smallest. And for any tree T, this satisfies this. And moreover, this algebraic connectivity of Pn is simply 2 times 1 minus cos pi by n. This Pn means a path on n vertices. And this is proved by Fiedler. And therefore, 2 times 1 minus cos pi by n is just a lower bound for the algebraic connectivity of trees on n vertices. And this lower bound is achieved by Pn. Now, what is the characteristic edge? Let's see. Suppose that Z is a graph on n vertices. Now, recall that 1 is an eigenvector of L corresponding to the eigenvalue. And then 1 transpose X is 0 for any Fiedler vector X, that we know. Therefore, the sum of these entries of X is equal to 0. That means these Xi's cannot have the same sign. That means they cannot be all positive or all negative. That means there has to be an Xi which is positive and has to be an Xj which is negative. Okay. So that is what we have. And in particular, if Ij is an edge and Xi times Xj, Xi means the ith entry of X, the vector X. If Ij is an edge and Xi times Xj is less than 0, then this edge Ij is called characteristic edge of the graph. And then a vertex k of Z is called a characteristic vertex if xk is 0. Xk means kth entry in X. Xk is 0, and there exists a vertex I which is adjacent to k such that xi is non-zero. Then the vertex k is called a characteristic vertex. Here is an example. This is a graph, and this is a Fiedler vector. We can see that this entry is 0, and these two vertex corresponding entry is non-zero. So this is a characteristic vertex. And similarly, x2 entry is negative, x6 entry is positive. So this is a characteristic edge. Here I give the entries. So this part, at this vertex we have positivity, negativity, we have positivity here, and this is 0. We have a non-zero vertex here. This is a characteristic vertex. This is a characteristic edge. Now, this is a very crucial, very interesting property. The subgraphs induced by positive vertices are all connected. Similarly, the subgraph induced by negative vertices are also connected. Now, what is this positive vertices and negative? Positive means non-negative actually. Suppose X is a Fiedler vector of a connected graph. Now consider V plus to be those vertices I of Z whose corresponding entries in the Fiedler vector are non-negative. Similarly, V negative is like. And the subgraph induced by this V plus is connected. Similarly, subgraph induced by V negative is also connected. How? Let's have a proof of this. Suppose without loss of generality, these are the vertices belonging to V plus. Okay, and the subgraph induced by say V plus is disconnected. Suppose assume that we are trying to prove it by the method of contradiction. This is disconnected. And say without loss of generality, so we have at least two components. Say these are 1 to 2 R, say these are the vertices from which to these vertices there is no edge in between. Then the Laplacian matrix can be partitioned like L1, 0, and this is a 0 matrix, not the value 0. Some block matrix like this. So where L1 is R by R matrix, L2 is K minus R times K minus R. Now suppose X equal to the Fiedler vector X is like this. X is just partitioned accordingly. Okay, whatever be the order of L1, order of X is like this. Similarly, Y and Z. These are not simply X, Y, Z. These are vectors X, Y, Z. Then by just this equality, it gives us L1X plus NZ equal to this. And you observe that this N is negative, less than or equal to 0. Z is also less than or equal to 0. Because this contains minus ones only. And NZ, that's why is greater than or equal to 0. Also, since Z is connected, that implies that N has at least one non-zero entry. And that says that this NZ can never be 0. And therefore, from 1, it follows that this quantity is minus NZ is less than or equal to 0. And NZ is no, since NZ is non-zero, so I have this non-zero. Therefore, X transpose L1 minus AGIX is less than or equal to 0. And you note that this is a standard, one can easily see this. Whenever X transpose MX equal to 0, that implies MX equal to 0, and MX equal to 0 implies this equal to 0 for any positive semi-definite matrix. So using this, we can say this. Now, if L1 minus AGI is a positive semi-definite matrix, then we must have this. This is by the definition of positive semi-definite. And then by S1, we will have this times X equal to 0. But this is a contradiction to the equation number 2. Therefore, L1 has an eigenvalue which is smaller than AG. Okay. Similarly, we can see that L2 has an eigenvalue less than it. That's the second smallest eigenvalue of AG plus a second smallest eigenvalue AG plus of this has to be less than AG. Now by Cauchy's, using Cauchy's interlacing theorem, Cauchy's interlacing theorem tells us that AG is less than or equal to AG plus 1. But that's a contradiction to this fact. That's why we are done. The subgraph induced by V plus should be connected. Similarly, we can prove that the subgraph induced by V negative are also connected. Now, this is a very, very interesting property, monotonicity in the Fiedler vector for a tree. Now, what it says, now suppose that X is a Fiedler vector of a tree, and say T is a tree on n vertices, then exactly one of these two occurs. What is? No entry of X is 0. And in this case, there is a unique vertex, unique characteristic edge. And suppose that this Ij is a characteristic edge such that Xi is greater than 0, Xj is negative. Then along any path in T that starts at I and does not contain J, the entries of X increases. And similarly, along any path in T which starts at J but does not contain the vertex I, decreases. So I missed that sentence here. No, I did not miss. Also, along any path T which starts at J does not contain I, the entries of X decreases. So either this happens or the next one. Now, suppose some entry of X is 0. Now, in this case, the subgraph, this should be subgraph induced by the 0 vertices is connected. And there is a unique characteristic vertex. Suppose that characteristic vertex is K. And along any path that starts at K, the entries of X either increase, decrease, or maybe identically 0. That may happen. So here is an example. This is a tree, and I have no entry of x0. That means this is a characteristic edge, and one can see this. These are the entries of the Fiedler vector. One can see this. This is positive, and see along this path, which does not contain this vertex, the entries are increasing. Now this is negative. You can see entries are in decreasing order. Here also it is in decreasing order. Now this is an example which have a characteristic vertex. This is a characteristic vertex, the red one, and its entries are like this, 0. See, this is along this path we are having, from this one we are having increasing, we are having decreasing along this path, identically 0, and along this path onwards it is decreasing. These two situations can only happen, and this says that in a tree I can have only one characteristic vertex or one characteristic edge. If it has a characteristic vertex, it cannot have characteristic edge. Similarly, if it has a characteristic edge, it cannot have characteristic vertex. Only one possibility is there. Now that this type of concept can be taken in a more generalized way. Suppose that Z is now any connected graph, then what can we say? Can we say something similar? That is the next question one can ask. Now these things are due to Fiedler. This I forgot to mention. These are proved by Fiedler. He has proved way back in 1970s. Now, what is a pure path? Suppose that this is a graph Z. A pure path is a path that contains at the most 2 points of articulation of each block. Points of articulation means cut vertex. So, at the most 2 cut vertex can be present in a path from a block. Here, for example, this is a pure path. Similarly, this is another pure path. Now, Fiedler's monotonicity theorem. This theorem again is proved by Fiedler. Now, what it says, say X is Y is a Fiedler vector of the graph Z, then either this case A happens or case B happens. Now, what is case A? Case A says that there is exactly one block B in Z which contains both positively and negatively valuated vertices with respect to Y. And every other block has either vertices with positive valuation only or negative, or vertices with negative valuation only, or vertices with 0 valuation. And every pure path P which starts at a vertex I of B and contains no other vertex of B has the property that the valuations at the points of articulations contained in P is either in increasing order or decreasing or a 0 along that path. And that depends upon whether Yi is positive, Yi is negative, or Yi equal to 0. If Yi is positive, then along that path, the valuations at the cut vertices increases. If Yi is negative, then valuations at the cut vertices along that path decreases. And if Yi is 0, then along that path, the valuations at the cut vertices are identically 0. This is case A. And the case, what does case B say? Case B says that no block of Z contains both positively and negatively valuated vertices with respect to Y. And in this case, there is exactly one vertex Z which has valuation 0. And this vertex has to be adjacent with a non-zero valuated vertex. And this vertex is nothing but has to be a point of articulation. That means cut point. And each block that contains, except that vertex Z, is either vertices with positive valuation only, or vertices with negative valuation only, or vertices with 0 valuation. And every pure path P which starts at Z has the property that, again, the similar kind of increasing or decreasing depending upon positiveness. Now, with an example, we will see. And type 1 graph, what are these? A graph Z is said to be a type 1 graph if it is a graph which satisfies case B. And type 2 graph if it satisfies case A of that Fiedler's monotonicity theorem. Okay, so a graph can be either type 1 or type 2. So for example, this is a graph. This is an example of a type 1 graph. So these are the entries of the Fiedler vector. Now we see that this is a vertex 0, which is a characteristic vertex. And one can see that along this path it increases. Along this path it decreases. Then I have another example. Here, this is a characteristic edge, this is a characteristic vertex. Now again, I want to point out, in case of a tree, characteristic, we can have only one thing. Either we can have a characteristic vertex or we can have one characteristic edge. But that is not the case with a graph. A graph can have characteristic vertices, can also have characteristic edges. Here we have seen. This is a graph which have a characteristic vertex as well as a characteristic edge. Why it is a characteristic edge? This says this end is negative, this end is positive. And this is a 0 vertex and it is adjacent to a non-zero vertex. And the Fiedler's theorem, you can see along this part we have decreasing thing because this is negative. And along this part we have increasing because this is positive. And here another example. You have this graph. This is a characteristic edge. And also it has no other characteristic. And this is a pure path. One can see that along this path, things are decreasing. Okay. But whereas along this, if we cannot consider this thing. This vertex, this vertex, this vertex, this vertex. This vertex. Why? Because that is not a pure path. It's a pure path. Sorry, it is a pure path, but the theorem says only about the cut vertices. Luckily, here I have this bigger than this. Theorem says that in a pure path, at the cut vertices only, things are increasing or decreasing, something like that. Now, what is the characteristic set? So we are towards the end of our lecture. So what is a characteristic set? Characteristic set is nothing but the set of vertices, characteristic vertices, and the set of characteristic edges of a graph is known as the characteristic set of the graph. Characteristic set contains all the characteristic vertices and the characteristic edges of the graph. Now suppose Z is a connected graph of order n and size m, and say X is a Fiedler vector of Z and S is the characteristic vertex of Z. Then either S is a single vertex or S lies in a single block. That means all the characteristic vertices or edges can belong to only one block. It cannot happen that, okay, some characteristic vertex is in one block and some characteristic is from some other block. It cannot happen. Okay. And that type of block is usually known as characteristic block. And the cardinality of the characteristic set is clearly less than or equal to m. It is proved m minus n plus 1. Now, if we have a tree, Z to be a tree, then this m is n minus 1. So I will have simply cardinality of S equal to 1. Now, this is a crucial property by Bufford, Cartel, and Potty, which says this. Now, can it happen that for one Fiedler vector, case A of the Fiedler's monotonicity theorem holds, and for another Fiedler vector, case B holds? The answer is no. They have proved it. That cannot happen. That means for any Fiedler vector, the graph has to be case A if it is case A for one Fiedler vector. And suppose that case A holds for each Fiedler vector of a graph. Then do we get the same characteristic block for every Fiedler vector? The answer is yes. And they have answered it. And similarly, suppose that case B holds for each Fiedler vector. Then do we get the same characteristic vertex? The answer is yes. They have answered this. Proof are lengthy, so I will not be able to complete it one like that. So I skipped it. And with this, I end, and these are my references. Thank you for hearing me. I end this talk here. Thank you. If any questions, one can ask.
Thank you so much, sir, for this wonderful session on the algebraic connectivity and field vector of graphs. Hope that our participants enjoyed this session and they got a lot of information about this topic, and they can use this information in their research. So we have one question raised by the participant. What are the applications of the Laplacian matrix in real life?
Real life, that I cannot exactly say, but it has a lot of applications in networking and all that I have seen.
Okay. And there are different kinds of matrices called Laplacian, random walk Laplacian. So how we can differentiate?
I have no idea about all those random. I have to see those. I have studied this Laplacian matrix only. So I have to see them if there is there.
Okay. So thank you so much, sir. It was really a pleasure for me to host you. So on behalf of the Department of Mathematics and our college, we are grateful to you, sir, for accepting the invitation.
Thank you.
So dear participants, hope you all got benefits from all the technical sessions. Those who have already doing their research in graph theory might have enhanced their research skills in some of the topics. And those who are still studying their undergraduate and postgraduate courses are motivated to take up the research career in graph theory. Of course, graph theory is a very broad discipline and cannot be learned in a single day. But we believe that today's talks by 3 experts in the field of graph theory have increased your curiosity to research more on the applications of graphs. Now we are at the end of the webinar. I would like to call Dr. G.D. Narayana, the Honorable Principal of Shri H.D. Devegowda Government First College, for valedictory address. Over to you, sir.
Okay. Good evening, Dr. Ismail sir, Senthil sir, and Devajit Kalita sir. And my dear organizers of this program, Dr. Vijay and Darshan, and also my dear delegates. It's my pleasure to give a valedictory address of the international webinar on the applications of graph theory, organized by the Department of Mathematics, Sri H.D. Devegowda Government College, Padavola, Hecke. I'm happy to know that this webinar is registered with more than 500 delegates from India, Bangladesh, China, Malaysia, Philippines, France, Nigeria, Pakistan, and Oman. It is interesting to observe that more than 50% of the delegates, faculties and research scholars working in the various institutions in those countries. In fact, the delegates not only from the mathematics background, delegates with the background of commerce, arts, business studies, physics, and engineering. This makes me feel that this branch of mathematics, the graph theory, has rolled out in almost all disciplines. This is not first time that our college is organizing the webinars. Every year, all the departments of our college organize national and international webinars to meet the global expectations. Our institution has recently reaccredited with B++ grade with a 2.96 CGPA on a 4-point scale. Since the past decade, this college is serving in the field of education and research by training students to compete at the global level. This college is within the top rank among the government colleges of Karnataka under the new parameter of NAC. I hope that the three speakers, Dr. Ismail Naci Cangül, Professor of Mathematics, Bursa Uludağ University, Turkey. Dr. Senthil Thilak, Assistant Professor, Department of Mathematical and Computational Sciences, NIT Karnataka. And Dr. Devegowda Kalita, Assistant Professor, Tejpur Central University, Assam, have delivered the excellent talks on the applications of graph theory and enhanced the research skills among our students and delegates. I would like to give special thanks to Dr. Raju K. George, Dean R&D, Dean IPR, and an outstanding professor of the mathematics in the Institute of Space Science and Technology for his inaugural address at this webinar. I hope that all participants benefited with the international webinar. I wish many more success to Department of Mathematics to conduct such webinars. And also, I especially would like to say thanks to all three special resource persons. Once again, I would like to say the name, Dr. Ismail ji, Dr. Senthil sir, and also the Dr. Devegowda Kalita sir. I heartfelt thank to you for our invitations. So I have no other than this, my body language and also the thanks, sir. Once again, all the best. Thank you, one and all, sir.
Thank you.
Thank you so much, sir, for your valedictory address. Now I request Dr. Vinay Kumar, sir, the head of the Department of Mathematics, propose vote of thanks.
Good afternoon, one and all. As we know that every new beginning has an end, here we come to an end of international webinar on the applications of graph theory. It's my proud privilege to pronounce heartfelt thanks to each and everyone. First of all, let me thank Professor Raju K. George, eminent professor from Indian Institute of Space Science and Technology, for his inaugural address. On behalf of the department and the college, we thank you very much, sir. And today's speaker of the first technical session, Professor Ismail Naci Cangül of Bursa Uludağ University, Turkey, on some recent applications of graphs. Sir, we extend our heartfelt thanks from the department and the college administration for sparing your precious time. Thank you, sir. Now, I extend my wholehearted thanks to Professor A. Senthil Thilak of NIT Karnataka for delivering the talk on graph theory in brain network analysis. Thank you very much, madam. The last technical session now, the webinar which was delivered by Professor Devegowda Kalita of and the college administration. Thank you, sir. Not but the least, I extend my heartfelt thanks to the president and principal of our college for all his support and encouragement. Thank you, sir. At the last, I extend my thanks to each of the participants across the world for taking part in this webinar and making it a grand success. Thank you, each and everyone. And let me thank all the one who has supported us in organizing this event. Thank you, one and all. With this, I conclude my vote of thanks.
Thank you, sir, for proposing the vote of thanks.
Vijay,
Yes, sir.
please give me a 1 minute to me.
Yes, sir. Yes, sir. Proceed,
I'm
sir.
sorry, I forgotten the one icon name, Dr. Vinay sir. I would like to say thanks on behalf of this grand success. Vinay ji, thanks to you. So nice. So, okay, sir. For the conduct a very good intellectual program. So, Vinay ji, once again, I would like to say thanks to Vinay also. So, thank you.
Yes.
Thank you, sir.
Thank you, sir. So, dear all participants, You will receive the e-certificates to your email address after submitting the feedback forms. The link to submit the feedback form has been already shared here and also to the WhatsApp group. Hope all of you enjoyed the webinar. Thank you all for your active participation, and we look forward for your participation in our future events too. That's all from here. All the very best to your future endeavors, and God bless you all.